Welcome to part 2 of our image counter case study. In this second part of the lesson, we're going to take a look at how various flux, mono, and scheduler operators from Project Reactor can be applied to a program that crawls a hierarchical folder structure recursively to count the number of images starting at some designated root URI. In particular, we're going to focus on the methods and fields that are provided in the image counter class. And we'll also take a look at the end of this video at a unit test that puts all the pieces together and runs them in practice. We're now in the IntelliJ project for my image counter case study. Let's start by taking a look at the main class, which of course provides the main entry point into this test program. As you can see, the first thing we do is we initialize the option singleton by passing it any command line arguments that may have been provided, and that will be used to set various option values that are used through other parts of the program to direct the way it behaves. We then go ahead and make an instance of image counter, passing in the root URI from where the traversal will begin, which could either be locally or it could be connected to the web. Let's now go ahead and take a look at the image counter class itself. As you can see, there's several fields that we use here. The first field we're going to look at is called mUnique URIs, and that is basically a thread-safe cache of URIs that have already been processed, so we don't try to double count them. This is implemented by something called a concurrent hash set, which is a class I implemented as a simple wrapper around concurrent map or concurrent hash map, as the case may be. You can see down here, we make it a concurrent hash map, but it only provides support for keys rather than key value pairs, which is what a map does. The most important method in concurrent hash set is called put if absent. And what this does is it uses the underlying concurrent hash maps put if absent method, which will atomically check to see whether or not an item is already in the map. And if it is, it'll just go ahead and return true. If it's not, it'll add it atomically and return true. So it's just a way of being able to check atomically from different threads to see whether or not we've already visited an existing URI. So let's pop back over here and look at a couple more fields. The next field we have is called S0, and this is a mono to an integer, which is just assigned a value of 0. So it's just used as a 0, essentially a 0 constant. And then the final field we have here is called S timeout duration, and this is used to define a 10-second duration to wait for all the operations to complete running asynchronously. So if the crawl takes more than 10 seconds, then we're going to drop out. Otherwise, we're going to basically get the results back, assuming everything works. We have a default constructor that's used for our test program that we'll look at shortly. Here's the other constructor. This is the one that's passed in a root URI, which is where we want to start our traversal. And that's where we're going to begin our detailed walkthrough of the code itself. As you can see here, we're going to call a recursive method called count images. You'll see how it's recursive here in just a bit. And we're going to start by passing it in the root URI where we want the traversal to begin, and then an initial depth count of 1 because we're at the root. We will then call the block optional method, which will block for the timeout duration, either waiting till we encounter an error, till the whole thing processes completely and successfully, or the timeout occurs. At the end, we're going to go ahead and print out the results, which will indicate how many images were counted from our traversal from the root. You can see that block optional returns an optional to an integer, and that's why we use total images dot or else, which either gives the number if we had a present value in the optional, or it'll return 0 in this case. So now let's go ahead and take a look at count images. And this call is going to be used recursively, and we'll see how it gets used. And what it does is it starts from a given page URI, which could change as we traverse throughout the structure, and it'll go up to a certain depth. So what we do here is we first do a little sanity checking. We see if the depth is greater than the max depth using our option singleton to avoid having to clutter the parameter list for this method with lots of other parameters. So we use the options instance max depth method to say, have we exceeded the max depth? If we have, we're just going to return the 0 mono saying we're done and there was no count here at all. Otherwise, we then go ahead and use the conditional check then act operator put if absent, which we define on our concurrent hash set, which uses the concurrent hash maps put if absent method under the hood. And that checks to see whether or not we've already seen this URI before. If we haven't, we're going to continue. But if we have seen it and it returns false, then we're also going to return 0. Finally, if we get through those sanity checks, we are going to then call another helper method called count images async. And that will asynchronously, in parallel, count the number of images at this page URI as well as also recursively crawl any other hyperlinks that are accessible via this page URI and count the number of their images as well. And then eventually what it'll do is give you back a mono. And if all goes well, then we're going to print the total number of images that were encountered at this given depth. So let's go ahead and take a look at count images async. So count images async is this helper method, and it really does the asynchronous parallel computing that's so cool and so much a part of what monos can provide you. So the first thing we're going to do is we're going to have a call to get start page, which is a little helper method. And that, as you see, is going to return a mono to a document. This is going to use the JSoup parsing library for HTML. So let's go ahead and take a look at get start page. So get start page is going to use the from callable factory method operator on mono, and it's going to go ahead and call down to get a page using JSoup. So I wrote a little wrapper for JSoup that allows us to hide whether or not we're doing something on the local file system or remotely over the web. So all we have to do is just say get page, pass it a URI, and it'll take care of all the magic under the hood to use the appropriate JSoup calls to get the content that we're requesting. Now, as we had seen before in part one of this video when we talked about the transform deferred operator, we're going to go ahead and run this computation in a background thread, and that background thread will come out of the common fork join pool. And we do this by calling the common pool mono helper method in the React Utils class, and that will use the subscribe on method for mono in order to be able to schedule the computation to run in the common fork join pool. So this is that cool transform deferred operator we talked about before. So what we're basically doing here is we're starting an asynchronous download in the background. And what we get back from that is something that's called a mono to a document being a JSoup data structure. And we use var here, which is I think it's a Java 10 feature that allows you to omit the return or allow you to omit the type of values that are returned from methods. So in this case, we just say var page mono, but IntelliJ tells us it's really a mono to a document, in case you were curious. What we do now is we now take this mono, and when that asynchronous computation completes, two things will start to run in parallel. And one of them is going to be this little mono chain, and the other is going to be this little mono chain. Both of these things will run concurrently, and they're both going to be using the common fork join pool. And you can see if you take a close look at this, they're both using transform deferred and the React Utils common pool mono factory method to get the appropriate context in which to run these computations in parallel. Let's take a look at this one first. This first arm of the parallel processing, which is kind of like forking, if you will, asynchronously counts the number of images on this page and returns a mono that will emit that count when all the asynchronous processing is done. Down here, the second arm is going to asynchronously count the number of images that can be linked on this page or found by links, hyperlinks on this page, and it returns a mono that will emit that count when it's completed. So both those things will go on at the same time. Let's take a closer look at what the first arm of this fork does. It's going to use the map operator to call get images in page. And what get images in page does is it simply uses the JSoup select method to find all the image elements that are tagged as images on the page. So we're going to get back basically a data structure called elements, which is basically a collection, like a list or set. And that will then allow us to know the contents that are in fact images. We'll have that information. All that computation will be done in the background. And when we're done, we're going to go ahead and count the number of images by using the list : size method reference. So what we're going to get back here is a mono that counts the number of images that were on that page. Down here, the second arm of this fork is where we're going to use flat map. So this flat map will be called when we've got the asynchronous contents of the page downloaded. And it's going to go ahead and call another helper method called crawl links in page. And you can see we pass in the page and the depth. What crawl links in page does is quite interesting. It goes ahead and it uses the from iterable factor method defined on the Flux class to select all the hrefs. So we go out and we say, does this page have any hyperlinks in it? And if the answer is yes, we're going to basically get a flux of them. And then we're going to use the flat map operator on that flux to go ahead and use the flat map concurrency idiom. And what this will do is for each hyperlink on the page, we're going to do the following computation in the background using the common fork join pool, using our transform deferred operator. And we're then going to use flat map here in order to be able to recursively call count images. So if you recall, count images is kind of where we started at the beginning, where we check to see if we've exceeded the max depth, we check to see if we've already seen this URL, and if not, we call count images async. And so by calling count images recursively, we're then traversing one level lower in the tree of recursion in our hierarchy. And we indicate that by taking the current depth and adding one to that. So we go ahead and grab the URL that we've got, we convert it using JSoup to the appropriate information that's needed to do the traversal, and then we call ourselves recursively. When all of this processing completes, all these calls will take place in different threads in the common fork join pool. And when they're all done, whichever is the last thread is going to end up calling reduce. Now, if there were, in fact, actual hyperlinks on this page, then we're going to be reducing by taking the counts from each recursive traversal of each hyperlink. And then, as you can see here, we're going to sum them up together. However, if there were no hyperlinks on this page, then we're going to have an empty mono here, in which case we're going to use the default if empty operator we talked about in part 1 of this video to just return 0. So that's what the crawl links in page method does. You can see it's very sophisticated, very recursive, very asynchronous and concurrent and parallel and so on. And all of this stuff also will run in a background thread. Finally, we get two monos, one that's called images in page mono and the other called images in links mono. And we call the combine image counts method. And what combine image counts does is it uses the zip with combining operator on a mono to take the number of images in the page once that asynchronous computation completes, and the number of images in links reachable from that page when that asynchronous computation completes. And then it's going to go ahead and sum these things up together. So that'll end up returning us the final result. And you can see as this kind of pulls back out of the recursion, it'll propagate those results up through the monos. And when we're all done, we'll end up way back at the beginning of this whole thing where count images async was called. And that in turn is going to be returned as the value of count images. So very powerful, very asynchronous, very reactive. And I think it does a nice job of kind of illustrating what you can do by combining various features. We're using monos here. We're using some fluxes. We're using a lot of asynchrony. We're combining with the common fork join pool. And the end result is a very nice, interesting program that gets the job done. Now that we've walked through the source code for the image counter case study, let's go ahead and take a look at a unit test to illustrate how it behaves in practice. This is in the test directory, and you can see it's marked as a test, and the particular test is called test count images. We go ahead and create ourselves an argument that will pass in as the parameter to parse args for our option singleton, which is just going to say basically turn on debugging. And then we're going to create a new image counter object and call its count images method, passing in the root URI, which will default to the local traversal in this case, with an initial depth of 1. And then we come down here and we use the step verifier, which is a nice feature that's provided with Project Reactor to test the reactive mono and reactive flux capabilities. So we're going to go ahead and create the counter so that it'll subscribe to the counter mono, which we created up here. And then we go ahead and use some step verifier methods to verify what we expect the results to be. In this case, we expect the result to be 21 because we have 21 images that are going to be traversed by the default configuration. And then we expect to get a complete signal when we're done. And then we just verify that everything worked the way we expected. So if we go up here and we run this program, run the little test program, it should go ahead and start up, start cranking away. And if all goes well, we'll see the results here in just a second. So here are the results from our program. As you can see, it worked. It didn't blow up. And it printed out some diagnostic information that we had set the max depth, so it didn't go as far as it could have. We bounded it at depth of 2. We found 7 images in one of the folders. We found another 7 images in another folder, and then we found yet another 7 images elsewhere. So the final result was 21. And if you're curious what the results look like, if you want to see how to find what the results are, just come over here into the resources portion of the program, and you can see all the images that we traverse for this particular configuration, which are just images I have in my folder. There's also a way to do this using a web-based approach, which goes to my website and does essentially the same thing, but the images at my website are the same as the images on my machine. So I did them locally just to keep it running in a more timely and low latency manner. So that's the end of our walkthrough of the image counter case study, and also showing how to run it and demonstrating how you can use the test features of Step Verifier for the image counter case study.